Let's imagine that we've got some water waves and we're standing here watching these water waves go by us. Let's imagine that the waves have a wavelength of 2 meters, so each wave has a length of 2 meters, and they have a frequency of, let's say, 3 hertz. In other words, 3 waves pass us every second. Well, in 1 second, what length of wave will pass us by? In 1 second, 3 waves will pass. Each wave is 2 meters long, so what length of wave? Well, that would be 6 meters. 3 waves, each one 2 meters long, that must be 6 meters of wave would pass us. Well, if 6 meters pass us every second, how fast are these waves traveling? They must be traveling at 6 meters per second. But how did we get that 6? The 6 was just lambda times f. And if it's traveling at 6 meters per second, that must be the speed of the wave. This is a very, very general result that pertains to any kind, that applies to any kind of wave. And that is, if we take the wavelength times the frequency, that equals the speed of the wave. What's the speed of the wave if we're talking about light? It's c. So we have a very, very simple relationship between the wavelength of a light wave, the frequency of a light wave, and the speed. Now sometimes I'll refer to these electromagnetic waves as light waves, but sometimes light is usually reserved for just things that you can visually see. However, there's a lot more in the electromagnetic spectrum in electromagnetic waves that we cannot see. Let's take a look at what all of those waves look like. Here's a diagram that shows all sorts of different electromagnetic waves, where the frequency of those waves are shown up here on the top of the plot, and the wavelength is shown on the bottom. But at any of those waves, you can always multiply the frequency and the wavelength, and you'd get the same value, c, 3.00 times 10 to the 8th meters per second. The amount of the electromagnetic spectrum that we can actually see is just this small band right in the middle. The part of the visible electromagnetic spectrum are the colors that we see, that we sometimes label as red, orange, yellow, green, blue, indigo, violet. That's the visible part of the spectrum, or visible light. However, there's a lot more of the electromagnetic spectrum than we can see. To the left, in other words, longer wavelengths, shorter, smaller frequencies. Notice that as the wavelength increases, the frequency decreases. And as wavelengths increase, frequencies, I just said that again. And as wavelengths decrease, the frequencies increase. So for longer wavelengths, lower frequencies, from red light, there's infrared. And then longer wavelengths than infrared are radio waves. On the shorter side, wavelengths that are shorter than violet, there's ultraviolet. And then shorter than ultraviolet are X-rays. And shorter than X-rays are gamma rays. Now these cutoff divisions are not really solid divisions. There's nothing particularly different between short X-rays and long gamma rays. I mean, it's kind of a very nebulous sort of division, but these are approximate divisions here. Let's stick some numbers in here. For red light, let's imagine we know the frequency of a particular kind of red light, and again, there's no sharp division of what's red, what's orange, what's yellow, etc., etc. So let's imagine we've got a particular frequency of red light that we're thinking about, say 4 times 10 to the 14th hertz, and we want to figure out what's the wavelength of that particular frequency. Well, if lambda f equals c, we know lambda equals c over f, which is 3 times 10 to the 8th meters per second, divided by our frequency, let's say 4.00 times 10 to the 14th hertz. Divide that out, 1 over seconds cancels the hertz. Remember, the hertz is cycles per second. We'll kind of just drop off at cycles, which gives us, 7.50 times 10 to the minus 7th meters. The units of light are often written in a different form of meters. 7.5 times 10 to the minus 7th we can write as 750 times 10 to the minus 9th meters. And 10 to the minus 9th meters, a nanometer, is a common unit that's often given for the wavelength of light. So in this case, 750 nanometers. Visible light goes from around 400 to 800, very approximately, nanometers. It's kind of just a very general rule of thumb to help remember where they are. And then the longer end, the red light, is more towards the longer end. And then let's look at violet. Let's say we have a wavelength of violet that is, say, 380 nanometers. In other words, 3.80 times 10 to the minus 7th meters. And let's say we want to figure out what the frequency for that is. Again, lambda f equals c, so f equals c over lambda, or 3 times 10 to the 8th meters per second, divided by 3.80 times 10 to the minus 7th meters. Divide that out, and we get 7.89 times 10 to the 14th hertz. Very good. So we can use that result, lambda f equals c, to go either way. We could use it if we know lambda to figure out f. If we know f, we could use it to figure out lambda. Very good. Now, one thing or another thing that light has is energy. It carries energy with it. Let's take a look at that. Let's imagine that we have some electric field. Perhaps this electric field is being created by some positive charge. Maybe there's a positive charge over there or something like that. That doesn't matter. Let's just imagine we have some electric field, E. Anytime we have an electric field, there is energy stored in that electric field. And that energy has a density. And we'll call this the electric field energy density. We'll write this with a U sub E. This is the electric field energy density, and we'll see in a second we'll also have a magnetic field energy density. The units of this energy density, if you remember density back from 1111, we had a mass volume density, which was the mass per volume and had units of kilograms per cubic meter. In this case, we're talking about an energy density. The units of the energy density are joules per cubic meter. What this means is that any time we've got an electric field in the space, there is energy in that space. And the amount of energy per space that we have in that electric field is given by this quantity, the energy density. The value of the electric field energy density is 1/2 times epsilon naught times the electric field squared. Let's imagine we have an electric field of, let's say, 1 Newton per Coulomb. Let's figure out how much energy we have stored in the electric field. That is 1/2 times epsilon naught, 8.85 times 10 to the minus 12 Coulomb squared per Newton meter squared, times E, which is 1 Newton per Coulomb squared. 1/2 epsilon naught E squared. Multiply that out, we get 4.43 times 10 to the minus 12. And then let's look at what are the units here. We have Newton squared divided by a Newton. That leaves us with a Newton. We have Coulomb squared on the bottom, Coulomb squared on the top. They cancel out. And then we have per meter squared on the bottom, newtons per meter squared. Let's multiply top and bottom by another factor of meter, so meter over meter. We end up with Newton meters on the top. What's a Newton meter? A joule. And meters cubed on the bottom. So we end up with joules per cubic meter, just as we expected. Well, let's look at this number. 4.43 times 10 to the minus 12. Tell me something about that number. It's very, very small. So for an ordinary everyday type electric field, 1 Newton per Coulomb, we're talking about a very, very small amount of energy stored in the electric field. So not very much energy in your average ordinary electric field. Great. What about the magnetic field? Now let's imagine we have a magnetic field, and maybe this magnetic field is created by a magnet or something like that down there. Again, that doesn't matter. Let's just imagine we've got some magnetic field. There is energy stored in the magnetic field. We have an energy density, which we'll write as U sub B, which is the energy density in the magnetic field. And again, the units of U sub B are joules per cubic meter. And the amount of energy stored in the magnetic field is 1 over 2 mu naught B squared. So it's kind of the same form as the energy density in the electric field. Remember, that was 1/2 epsilon naught times E squared. The energy in the magnetic field is 1/2 times 1 over mu naught times B squared. So rather than epsilon naught for the electric field, it's 1 over mu naught for the magnetic field. So 1 over 2 mu naught times B squared. Again, let's stick in a value for the magnetic field. We'll put in 1 Tesla, but let's just keep in mind, remember what we found before, that's actually a very, very large magnetic field. This is not your ordinary everyday magnetic field. This is a very large magnetic field. Well, let's put that in and see what we get. 1 over 2 mu naught times B, 1 Tesla, squared, multiply that out, we get 3.98 times 10 to the 5th joules per cubic meter. Well, notice that's a very big number. That's a lot of energy. But keep in mind, this is a lot of energy if we have a very strong magnetic field. The important thing to remember is that anytime you have an electric field or a magnetic field, or maybe both, there is energy stored in that field. There's energy in the electric field, energy in the magnetic field. And if you had both, electric and magnetic fields, then you'd have energy stored in both of them. Okay, very good. Now, back to electromagnetic waves. That's a situation where we do have electric fields and magnetic fields, but those electric and magnetic fields are changing. As the wave moves through space, we have a changing electric-magnetic field. What can we find out about that energy? Here we have that picture that we used for the oscillating electric and magnetic fields for a wave, and I've drawn it here on the board. So let's imagine we've got this electric field that's going up and down and up and down, and the magnetic field which is going out and in and out and in like that. Here I've drawn the magnetic field in blue. So try to imagine this is actually coming out and then into the board. So out of the board and then into the board, out of the board, into the board, like that. We know that the energy densities, and now in this case we've got an electric and a magnetic field, so the total energy density is going to be the energy density in the electric field plus the energy density in the magnetic field. In other words, 1/2 epsilon naught E squared plus 1 over 2 mu naught B squared. We're going to have energy in both the electric and the magnetic field. But let's think about this for a second. What's the energy density going to be, let's say, at that point right there? Now, this wave is propagating through space, so as the wave moves, the electric field and magnetic field at any point in space will be changing as that wave propagates through. But instantaneously, when the wave is right here, what's the energy right there at that point? Well, at that point, the electric field is 0 and the magnetic field is 0. So there is no energy density at that point. At this point, let's say, where we have a very large electric field and a very large magnetic field, we'll have a lot of energy in the electric field energy density and in the magnetic field energy density. But then at another point next to it, we'll have 0, and then a lot, and then 0. And notice, it doesn't matter what the direction of the electric and magnetic fields are. This only depends on the magnitudes of the electric and the magnetic field. So as the wave moves through space, we'll have points where there is 0 energy, and then points where there's a lot of energy, where the magnitudes are large. And those high energy and low energy points will be moving through space. Again, what is often useful is what's the average energy density. Well, the average energy density we can find by taking the average of this quantity. Well, in this case, keep in mind, the electric field, we might think of this as something like E naught sine omega t, while the magnitude of the magnetic field also might be something like B naught sine omega t. And we need to average those. Well, we've already done something like this. If we were to average this quantity, now we're not averaging the electric field. The average electric field would be 0 because it's just as much up as it is down. What's the average of E squared, the magnitude squared. Excuse me, well, we would have to average E naught sine omega t squared and B naught sine omega t squared. Well, E naught is a constant. We could pull that out. What's the average of sine squared? Well, we did that before when we were looking at the power used in an AC circuit. We know the average of sine squared is 1/2. So the average of this would be 1/2 E naught squared. Well, we can take that, we'll do the same trick we did before, take that 1/2, divide it into 2 factors of the square root of 2. We could write this as E naught over the square root of 2, quantity squared. And what's E naught over root 2? It's the ERMS value. We can write that as ERMS squared. And then what's the average of this going to be? That's going to be BRMS squared. Very good. So the average energy density we can write as U sub average, or sometimes this is written as U in brackets. We can write that as 1/2 epsilon naught ERMS squared, 1/2 epsilon naught ERMS squared plus 1/2 mu naught BRMS squared. Very, very good. Now there's one more thing that's very interesting about this, and that is for an electromagnetic wave, let's think about how strong these electric and magnetic fields are. Let's go back to our picture of the way we formed these electromagnetic waves.